Now, in this document, I just opened this section, core registers, and here you can see that these are the processor core registers, okay? And these core registers are actually residing under, okay, this Cortex-M4 core, okay, or Cortex-M processor core, okay? So here you can see that the registers from R0 to R12, okay, are general purpose registers. Okay, so that means, so I'll just write that, okay, R0 to R12 registers, okay, are for general purpose. Okay, so that means these registers are not to R12. You can use it for general purpose, like for data operation, data manipulation, to store data, okay, to store addresses, etc. And all the registers, all the core registers are 32-bit wide. Great, so now let's move forward. The register R13 is called as stack pointer. Okay, so I'll just write that. The register R13 is called as SP, that stands for stack pointer. So that means this register is actually used to track the stack memory. Okay, so I will talk about stack memory and the stack pointers in detail, okay, in the subsequent lectures, okay. But for the time being, just know that, okay, R13 is a stack pointer which is used to track the stack memory. And beside this R13 register, two more registers are mentioned. That is PSP, which stands for Processor Stack Pointer, and MSP, which stands for Main Stack Pointer. And these registers are called as banked version of stack pointer. Okay, so more on this I will cover later. So all these three are actually stack pointers, okay, but one among these will be active depending upon the mode of the processor, which I will talk later. Okay, so don't worry about that. So now let's move forward. Now the register R14 is called as the LR. LR stands for link register. Okay, so now what we'll do is we will go to the description of the LR and we'll read about that. Okay, so I'll just go to this link here, okay, and it takes me to the description of the link register. Okay, just read this sentence. The link register is register R14. It stores the written information for subroutines, function calls, and exceptions. Okay, on reset, the processor sets the LR value to this value. Okay, so now let's not give much stress upon this sentence, but this sentence is very, very important, that the register R14 stores the written information, okay, for subroutine, okay, or function call or exception. Let me explain the use of link register, that is LR. Let's take the case of function 1 and function 2. Function 1 calls function 2 in this case, and the function 1 is called as caller and function 2 is called as callee. Here, this is a place where function 1 calls function 2. In terms of assembly language, it is a jump to another address. That's why PC is loaded with address of function 2. That's how execution goes to the function 2. At the same time, what happens is the LR is loaded with the address of the next instruction. That's how processor maintains the return address. PC is loaded with new address, LR is loaded with the return address. And when the function 2 finishes here, it has to return to function 1. At that time, the saved LR is copied into PC. That's how PC jumps back to resume function 1. That's the use case of LR. So that's why LR is used during function call or subroutine call to link back to the caller. Let's see this with an example. Here I have a code, and this is our older code. Here you can see that this is a main function, and main function calls this function generate interrupt. And now let's analyze this with disassembly. Here is a place where the main code jumps to this function generate interrupt, BL. BL stands for branch with link. When you use branch with link, the link register gets updated with a return address. So what's the return address here? So this is a return address, isn't it? So this is the address of the next instruction. So whenever this generate interrupt function returns, the execution must continue from here. So that's why this value will get updated in LR. Okay, so now what's the value of LR? The current value of LR is something different. You can see here. Okay, and now let me activate this instruction stepping mode. Now let me do single step. So when I do single step, the control will go to generate interrupt. You can see that. Okay, but the LR is updated with the link address. To this address, the processor must return when it finishes the generate interrupt function. Okay, now let's see that. So now let's see where generate interrupt ends. So here it is. So this is a place where the generate interrupt function returns to the caller. Now look at the instruction. Instruction used is BXLR. BX stands for branch indirect. When processor executes this instruction, the value of LR is copied into PC. So that's how the execution control resumes back to the caller. You can see that. Let me keep a breakpoint here and let's run. So now you can see that the code stopped here. Now when I hit single step, this LR value is copied into PC. You can see that. Okay, so LR value is 22B and PC is this much. Now let me do single step. You can see that that value is copied into PC. Now, but you can see that here the value 22A is actually maintained as 22B. So that has got something to do with T bit of the XPSR register. Okay, so that's a use of LR. LR links back to the caller during function call or a subroutine call. And with that note, I would like to end this lecture. Let me know if you have any questions. I will see you in the next lecture. So now the next register here is R15. The R15 register is called as program counter. So you can just read about that program counter here. Program counter is register R15. It contains the current program address, okay, or it contains the current instruction to be executed. On reset, the processor loads the PC with the value of the reset vector. After reset, the processor automatically loads PC with the value of the reset vector, which is at this address in the memory map, isn't it? Great. And here there is one more interesting sentence. The bit 0 of the value is loaded into the EPSR T bit at reset and must be 1. Okay, so that is special meaning for this sentence, and this is not a right time to explore EPSR and the T bit. Okay, so I will take up this later. All right, so now let's summarize. The register R13 is SP. R14 is called as link register, and it is used to hold the return information during function call and exception handling. And the register R15 is called as PC, which holds the address of the next instruction to be executed. Great. So now let's move forward. All right. So in the core register, the next section is special registers, which I will cover in the next lecture. So far, we have explored about the general purpose registers, SP, LR, and PC. And now let's explore special registers. Okay, so there are 1, 2, 3, 4, 5 special registers. Let's first explore the program status register. Okay, the program status register you can explore from this section here. Okay, just click that. And here it is. The program status register, okay, as its name indicates, it holds the status of the current execution of the program, okay? And this is also 32-bit wide. Here you can see 0 to 31. And the interesting thing about this register is it is actually collection of 3 different registers, okay? Here it is. The program status register combines 3 sub-registers, okay? One is called as APSR, which stands for Application Program Status Register, which consumes only 5 bits, okay, out of these 32 bits, okay, inside the program status register. So you can interpret something like this. In the program status register, these 5 bits are called as APSR, interrupt program status register, that we call as IPSR, which actually consumes 0 to 8 bits here. So this is called as IPSR register, okay? And the execution program status register, that we call as EPSR, and EPSR consumes some bits in between from here to here, that is from 26 to 25, 24, and some other bits in between, okay? So this is collectively called as execution program status registers. So collectively, these 3 registers are called as program status register, okay? All right, so now what is the purpose of application program status register, that is APSR? So APSR contains all the conditional flags, okay, like negative flag, zero flag. So this you might have studied in the basic microcontroller or microprocessor programming in order to detect the result, whether it is negative or whether it is zero or any carry or borrow generation during arithmetic operation. Okay, you can make use of these flags. Okay, so these flags are actually part of application program register. Okay, if the current instruction execution resulted in any negative value in the ALU, then the negative flag will be set. And if the current operation results in zero value in the ALU, the zero flag will be set. And based on that, you take, decision in your assembly programming, isn't it? So these conditional flags will be useful when you do assembly level programming where, okay, you want to branch based on negative result, or you want to take some other decision on the zero or non-zero condition. But if you are programming in high-level languages, then we just don't care about this application program status register, okay? So if you are interested, you can always explore this document to know more about that, okay? Now let's go to the interrupt program status register, okay? Again, this actually doesn't give any useful information, at least from the perspective of our programming, okay? So just see what they say about this register. The IPSR contains the exception type number of the current interrupt service routine. All right, so what does that mean? It says that exception type number of the current interrupt service routine. Great. So now let's move forward to execution program status register. Okay, so in the program status register, so you can see the EPSR actually consumes some bits in between, right? So here the T bit is very important, so which we are going to discuss next. Okay, and here it is, execution program status register. So I'll just go to the T bit, okay, which is for thumb state bit. So what's the significance of this T bit of the EPSR? Actually, I have a separate video on this where I discuss importance of T bit of the EPSR, but let me explain in brief here, okay? So as you can see here, if T bit of the EPSR is set to 1, the processor thinks that the next instruction which it is about to execute is from thumb ISA, that is thumb instruction set architecture. If T bit of the EPSR is reset, that is 0, processor thinks that the next instruction which it is about to execute is from ARM ISA. So T-bit decides whether it is ARM state instruction execution or thumb state instruction execution. So since ARM Cortex-MX supports only thumb state, for ARM Cortex-MX processors, the T-bit of the EPSR should be maintained as 1. Remember that, okay? Otherwise, execution of instruction when T-bit is 0 will result in processor fault. Okay, so we'll discuss more on this later when we discuss about T-bit with some examples.